Picture this. Right now, as you listen, Earth is gliding through a cosmic breadcrumb trail left by something that doesn't belong here. 3I Atlas, an interstellar visitor from another star system, passed us in December. Scientists said we were safe. And we were, from the comet itself. But here's what they didn't tell you. Comets don't travel alone. They bleed debris, charged particles, electromagnetic dust, all of it hanging in space like invisible tripwires across our orbital path. We're about to walk right through it. Some researchers are quietly concerned about what happens when Earth's magnetosphere meets material that was never born under our sun. Subscribe and follow along, because I'm about to show you why some researchers are losing sleep over this. You know that feeling when you walk through a spiderweb in the dark? That invisible thing you didn't see coming, suddenly all over you, clinging to your face, making you question what else is out there that you can't detect until it's too late. Now imagine that on a planetary scale. Picture Earth, our home, drifting through space at 67,000 miles per hour, and we're about to walk face first into something we never saw coming. December 19th, 2025. Mark that date. That's when Earth made its closest pass to a visitor from beyond our solar system, an interstellar comet with the clinical designation 3I Atlas. The scientists told us not to worry. They measured the distance at roughly 270 million kilometers, about 1.8 astronomical units, if you want to get technical about it. That's the kind of distance that makes headlines say, "No threat to Earth," in reassuring bold letters. The comet came. The comet passed. Everyone breathed easy and went back to their lives. But here's the thing about comets. They don't travel alone. They're messy. They're cosmic litterers, trailing debris like a car with a bad exhaust system, except instead of smoke, they're spewing out dust, gas, ice particles, and charged plasma across millions upon millions of miles. When a comet heats up as it approaches the sun, the ice on its surface doesn't just melt like a popsicle on a summer day. It sublimates, which means it goes straight from solid to gas, skipping the liquid phase entirely. That violent transformation tears material off the nucleus and flings it into space, creating what astronomers call a coma, that fuzzy cloud you see in comet pictures, and a tail that can stretch for tens of millions of kilometers. 3I Atlas left behind a trail, a wake, an orbital breadcrumb path of interstellar debris marking exactly where it's been. And Earth? We're heading right into that path. Now, before you start building a bunker in your backyard, let me be clear about what mainstream science says. The official position, the consensus among astronomers and planetary scientists, is that this poses no physical threat to Earth. The density of particles in a comet's tail is extraordinarily low. We're talking about a few dust grains scattered across volumes of space, so vast that calling it a vacuum would be generous. Even when Earth passes through well-known meteor streams like the Perseids or the Leonids, we get a pretty light show and nothing more. The particles burn up in our atmosphere as shooting stars, harmless and beautiful, gone in a flash of ionized air. But 3I Atlas isn't your typical solar system comet. It's interstellar. It came from somewhere else, some other star system where the rules of formation were different, where the ice and dust that condensed into this frozen wanderer had a different chemical signature, a different composition, different properties we're only beginning to understand. The James Webb Space Telescope pointed its infrared eyes at this thing and found something unusual. The gas coma is absolutely loaded with carbon dioxide, with a CO2 to water ratio far higher than anything we see in comets born in our own solar system. That tells us this object formed in conditions unlike anything in our cosmic neighborhood. So, we have an interstellar visitor, already unusual, leaving behind a trail of material with potentially unique electromagnetic properties, and Earth is going to drift through the orbital path this thing traced across the inner solar system. The question isn't whether we'll encounter any debris. The question is, what happens when we do? Here's where the speculation starts getting interesting, and where I need you to keep your critical thinking hat firmly planted on your head. There are claims circulating online, spreading through forums and alternative science channels, that this isn't just about a few dust grains that'll burn up harmlessly. The theory goes that the charged particles in 3I Atlas's wake could interact with Earth's magnetosphere, that protective magnetic bubble that shields us from solar radiation and cosmic rays. Some are suggesting these interactions could trigger unusual atmospheric phenomena, affect our geophysics, maybe even influence weather patterns or seismic activity. The mainstream scientific community does not support these claims. Let me repeat that for absolute clarity. There is no peer-reviewed evidence suggesting that comet dust at these densities can cause the kinds of planetary scale effects being speculated about. The particle flux is simply too low. The energies involved too small compared to the natural variations Earth experiences from solar activity alone. But, and this is where it gets genuinely fascinating, we also don't have extensive data on what happens when Earth encounters debris from an interstellar comet. This is only the third confirmed interstellar object we've ever detected passing through our solar system. The first was Oumuamua back in 2017, that bizarre elongated thing that some people still argue might have been artificial. The second was Comet Borisov in 2019, which looked like a regular comet but came from interstellar space. 3I Atlas is number 3, and it's the first one where Earth's orbital path might actually intersect with material it left behind. Cometary dust can carry an electrical charge. When these particles are hit by solar ultraviolet radiation and the solar wind, electrons can be stripped away, leaving the grains positively charged. Charged particles don't just drift through space, obeying simple Newtonian mechanics. They interact with magnetic fields. They can be accelerated or deflected. They can clump together in unexpected ways. And when they hit Earth's upper atmosphere, they can deposit that charge, creating ionization that affects everything from radio wave propagation to the behavior of the ionosphere itself. Could this be significant? Could we see effects? The honest answer is probably not at any scale you'd notice in your daily life. But might sensitive scientific instruments detect subtle anomalies in atmospheric chemistry, in ionospheric behavior, in the flux of particles entering Earth's magnetosphere? That's actually possible. Scientists have measured increased concentrations of certain isotopes and dust types during meteor shower peaks. If Earth does pass through denser than expected debris from 3I Atlas, we might see similar signatures. The comet itself is now heading outward from the Sun, racing toward its next cosmic appointment. On March 16, 2026, 3I Atlas will make a close pass by Jupiter, the giant of our solar system, the planet whose gravity has protected Earth from countless impacts by deflecting or capturing asteroids and comets over billions of years. What happens when an interstellar interloper moving at 58 kilometers per second encounters Jupiter's immense gravitational field? What could that interaction tell us? What might it change? These are the questions keeping some astronomers up at night. Not because they expect catastrophe, but because we're in genuinely uncharted territory here. We're not just watching a comet. We're watching an object that formed around a different star, that carries within its frozen nucleus the chemical fingerprint of another planetary system, that's now careening through our cosmic backyard, leaving a trail we're about to step into. The wake is there. The debris is real. And as spring approaches, Earth will be in the right place at the right time to find out if there's anything in that wake worth worrying about, or at least worth noticing. So, what exactly is 3I Atlas? Where did it come from? And what is it really made of? Let me take you back to the moment astronomers first realized what they were looking at. When an object is spotted moving through space, scientists immediately calculate its trajectory, plotting where it came from and where it's going. Most objects in our solar system follow elliptical orbits, looping around the sun in predictable patterns that repeat over years, decades, or millennia. Some are nearly circular, like Earth's orbit. Others are extremely elongated, like the comets that swing in from the distant Oort cloud, get a gravitational slingshot around the sun, and disappear back into the dark for thousands of years. But 3I Atlas? Its trajectory is hyperbolic. That single word changes everything. A hyperbolic orbit means this object is not bound to our sun. It's not coming back. It came from somewhere else, passed through once, and will continue into the galaxy never to return. The mathematics don't lie. When you plot the orbital parameters, when you measure the velocity relative to the sun at about 58 kilometers per second, you get numbers that could only come from an object originating outside our solar system. This thing is genuinely, unambiguously interstellar. The comet reached perihelion, its closest approach to the sun, on October 29th through 30th, 2025, at a distance of approximately 1.36 astronomical units. For reference, Earth orbits at 1 AU, so 3I Atlas got a bit closer to the sun than we do, but not dramatically so. That solar heating is what triggered the sublimation, what woke up this frozen relic and caused it to start shedding material in earnest. Then came December 19th, when Earth and the comet reached their closest mutual approach, 270 million kilometers. In cosmic terms, that's actually quite a respectable distance. There was never any chance of physical collision. The comet itself, the solid nucleus at the center of all that gas and dust, probably measures just a few kilometers across. Finding that with your planet from 270 million kilometers away would be like trying to hit a specific grain of sand on a beach from the next city over while blindfolded. But now the comet is on its way out, heading deeper into the outer solar system, and on March 16th, 2026, it will pass through the region of space dominated by Jupiter's gravity. This isn't a close flyby in the sense of skimming the cloud tops. It's more about passing through Jupiter's gravitational sphere of influence, where that giant planet's mass can affect the comet's trajectory, possibly changing its velocity or path through space in measurable ways. So what is this thing actually made of? What secrets does it carry from its birthplace among alien stars? The Hubble Space Telescope captured images showing a teardrop-shaped cocoon of dust surrounding the nucleus. That asymmetric shape tells us about the direction of solar radiation pressure and the way material is being pushed away from the sun. But it's the James Webb Space Telescope, with its incredible infrared sensitivity, that really cracked open the mystery of 3I Atlas's composition. The spectroscopic data came back showing something remarkable. The gas coma, that atmosphere of volatiles evaporating off the nucleus, is absolutely dominated by carbon dioxide. Most comets we've studied from our own solar system have a much higher proportion of water ice. Water is typically the star of the show, the most abundant volatile, the thing that makes comets worthy of the nickname dirty snowballs. But 3I Atlas flips that script. Its CO2 to water ratio is extraordinarily high, suggesting this object formed in a region of its birth star's protoplanetary disk, where carbon dioxide ice could condense and accumulate in much greater quantities than water ice. That single fact tells us volumes. It means 3I Atlas probably formed farther from its parent star than most solar system comets formed from ours, in a colder region where different ices could remain stable. It means the chemical conditions in that distant stellar nursery were different from the conditions that prevailed when our own solar system was taking shape 4.6 billion years ago. Every comet is a time capsule, preserving the chemistry of the earliest days of planetary formation. This one is a time capsule from someone else's solar system entirely. The nucleus is icy, a jumbled mixture of frozen gases and dust grains, and as it heats up, that mixture sublimes away. The coma forms, expanding outward, And then solar radiation and the solar wind push on all that material, creating the tail. Actually, comets often have two tails. The dust tail, made of larger particles that follow the comet's orbital path, and the ion tail, made of charged gas molecules that get blown directly away from the sun by the solar wind, always pointing in the anti-solar direction, like a cosmic windsock. The dust grains themselves vary enormously in size. Some are microscopic, just microns across, barely bigger than the wavelength of visible light. Others are pebbles, or even larger rocky chunks. The smaller grains are affected more by radiation pressure, pushed outward faster. The larger grains stay closer to the orbital path. And here's the critical thing for our story. Larger grains, especially if they carry an electromagnetic charge, can persist along the comet's trajectory for extended periods. They don't get swept away instantly. They linger, tracing an invisible path through space. NASA's Stereo spacecraft and the upcoming Punch mission have been imaging the comet, tracking its activity, measuring the rate at which it's producing dust and gas. These observations help scientists build models of how much material is being ejected, how fast it's moving, and where it ends up in space. The models universally show the same thing. The density of particles in the comet's wake is extremely low. We're not talking about a cloud of debris thick enough to see or feel. We're talking about individual grains separated by thousands or millions of kilometers. But, and this is where the uncertainty creeps in, models are only as good as the data they're built on. We've never had detailed measurements of an interstellar comet's dust trail before. We don't know if interstellar dust behaves exactly like solar system dust. We don't know if there are clumps or streams of higher density that our current instruments can't detect. We don't know if the electromagnetic properties of these particles might make them cluster or align in ways that typical comet dust doesn't. What we do know is that even in ordinary meteor showers, which happen when Earth passes through the debris trails of known comets, we see variations in intensity that models don't always predict perfectly. Some years the Perseids put on a spectacular show. Other years they're a dud. The distribution of material isn't perfectly uniform. It's lumpy, chaotic, influenced by gravitational perturbations from planets over decades and centuries. So when Earth drifts through the region of space where 3I Atlas passed, we're essentially rolling the dice. Most likely, we'll detect nothing unusual at all. A few dust grains might create some pretty meteors. Sensitive instruments might pick up a slight uptick in certain atmospheric measurements. But there's also a non-zero chance, however small, that we encounter something unexpected. A denser stream, particles with unusual properties, electromagnetic effects that don't fit the standard models. And here's where things get properly weird, where the data stops being straightforward and starts developing edges that don't quite fit. Astronomers are trained to expect the unexpected. When you spend your career pointing telescopes at distant objects, you learn that the universe has a habit of throwing curveballs. But 3I Atlas has been throwing more curveballs than usual, displaying behaviors that are unusual even by comet standards, and that's triggered a feeding frenzy of speculation ranging from the scientifically plausible to the completely unhinged. Let's start with the legitimate anomalies, the observations that have made professional astronomers scratch their heads. Multiple observers have reported sunward jets, structures in the comet's coma that appear to point toward the sun rather than away from it. That's weird. Solar radiation pressure should push everything away from the sun. Seeing material streaming sunward is like watching smoke blow into a fire. There are explanations for this involving rotation, asymmetric outgassing, and complex gas dynamics, but it's not something you see every day. The comet has also shown rapid brightness variations, fluctuating in intensity over short timescales in ways that suggest changes in its activity level, or possibly rotation exposing different areas of the nucleus to sunlight. Some of these brightness changes have been dramatic enough that amateur astronomers with backyard telescopes have noticed them from one night to the next. Then there's the polarization data. When light reflects off dust particles, it becomes polarized, meaning the electromagnetic waves all align in the same direction. The degree of polarization tells you about the size, shape, and composition of the particles doing the reflecting. 3i Atlas has shown extremely high polarization in some measurements, suggesting dust grains with unusual properties or unusual size distributions compared to typical comets. That's interesting. It could mean the dust is fluffier, or made of different materials, or structured in unexpected ways. Now, all of these anomalies have potential natural explanations. Comets are complicated beasts. They rotate. They have jets on their surfaces. They break apart. They have volatile pockets that suddenly rupture and spray material into space. Unusual doesn't necessarily mean unnatural, but unusual does attract attention, and attention attracts speculation. Online forums and alternative science communities have latched onto these anomalies and run wild with them. One popular theory circulating suggests that 3i Atlas has exhibited pulsing light patterns that some interpret as artificial signals. Let me be extremely clear here. There is no credible scientific evidence for this claim. The brightness variations have natural explanations, but that hasn't stopped people from analyzing amateur photographs, frame by frame, looking for patterns, constructing elaborate theories about what these supposed signals might mean. Another thread of speculation involves X-ray emissions. Comets do emit X-rays when solar wind ions collide with neutral gas molecules in the coma, a perfectly natural process called charge exchange. It's been observed in many comets. But some people have taken normal X-ray detections and spun them into narratives about unusual electromagnetic activity, exotic propulsion systems, or energy sources that violate known physics. Again, no credible evidence supports these interpretations. Enter Avi Loeb, the controversial Harvard astronomer who's made a career out of asking whether interstellar objects might be artificial. After Oumuamua, Loeb co-authored a paper suggesting that objects' unusual acceleration could be explained if it were a light sail built by an alien civilization. The scientific community largely rejected that hypothesis, favoring more mundane explanations involving outgassing, but Loeb's willingness to consider exotic possibilities has made him a hero to those who want to believe we're being visited. 3i Atlas has naturally fallen into Loeb's crosshairs. While he hasn't specifically claimed this comet is artificial, his general advocacy for taking the search for technosignatures seriously has energized communities looking for anomalies in this object. The Breakthrough Listen Project, a well-funded initiative to search for signs of extraterrestrial intelligence, actually scanned 3i Atlas for artificial radio signals during its approach. They found nothing. Radio silence. Just the natural emissions you'd expect from a comet. That negative result should have dampened speculation, but if anything, it seems to have intensified it. Now, there are theories about why the signals weren't detected by radio telescopes, involving everything from different communication frequencies to deliberate concealment. This is where we enter the realm of unfalsifiable claims, where any lack of evidence is just evidence of absence being used as evidence of concealment. It's conspiracy thinking masquerading as scientific inquiry. Some of the wildest claims border on the absurd. Forum posts describe impossible jet behaviors, particles moving in directions that would violate conservation of momentum, energy emissions that would require physics we haven't discovered yet. Almost universally, these claims are based on misinterpretations of amateur observations, image artifacts, or simple mistakes in calculation. When professional astronomers with calibrated instruments look at the same phenomena, they see normal comet behavior. But let's zoom out for a moment and ask why this happens. Why do rare astronomical objects attract this kind of fringe speculation? Part of it is the genuine mystery. Interstellar objects are so rare, so poorly understood, that there's legitimate room for scientific uncertainty. We don't have all the answers. That gap between what we know and what we don't know is like catnip for speculative minds. There's also a deep human desire to find meaning, to discover that we're not alone, to believe that the universe is full of intelligence and purpose, rather than just rocks and gas obeying physical laws. When something unusual appears in the sky, we project our hopes and fears onto it. Throughout history, comets have been seen as omens, harbingers of change, messages from the gods. We've just replaced ancient superstition with modern mythology about alien visitors and technosignatures. Now, let's talk about the alleged wake, because this is where the speculation directly intersects with Earth. The theory goes something like this. 3I Atlas isn't just leaving behind inert dust and ice. It's trailing a cloud of electromagnetically active charged plasma that can interact with planetary magnetic fields and atmospheres. When Earth drifts through this wake, these interactions could trigger anomalous phenomena, geomagnetic disturbances, atmospheric changes, maybe even seismic activity through mechanisms involving electromagnetic induction in Earth's mantle. This theory is not supported by mainstream astrophysics. The particle density is too low. The energies involved are too small. Earth's magnetosphere is constantly being bombarded by the solar wind, a stream of charged particles from the sun that carries far more energy than anything a comet could produce. We experience geomagnetic storms when solar activity increases, but these require massive solar flares ejecting billions of tons of plasma directly at Earth. A comet's tail is trivial by comparison, but here's what makes the speculation persist. We can't prove it's completely impossible. Science works by building models based on observations and then testing those models against new data. Our models say comet dust trails don't cause planetary scale effects, but those models are based on observations of solar system comets, not interstellar ones. What if interstellar dust has properties we haven't accounted for? What if there are density variations or charge accumulations our instruments haven't detected? The scientific answer is to remain skeptical but open, to collect more data, to watch what happens when Earth moves through the projected debris path this spring, and to update our models based on what we observe. That's how science advances. But in the age of social media and instant information, that patient approach gets drowned out by sensational headlines and fear-mongering. Critical thinking requires us to distinguish between genuine uncertainty and baseless speculation. Yes, we don't know everything about 3I Atlas. Yes, there are observations that don't fit perfectly into existing models. But no, that doesn't mean the laws of physics are being violated or that we're facing some unprecedented threat. It means we have an interesting object to study, and studying it will teach us things. Still, even without exotic physics or artificial origins, the sheer rarity of this event means there's potential for discovery. We might detect subtle effects we've never seen before. We might learn something new about how interstellar material behaves. And when 3I Atlas reaches Jupiter in March, we might witness interactions between an interstellar interloper and a giant planet's magnetosphere that we've never had the chance to observe before. The mystery isn't about aliens or danger. It's about the opportunity to expand our knowledge at the frontier of what we understand about the cosmos. But to really grasp what might happen, we need to dive into the actual physics of dust and electromagnetic fields. Let me walk you through how this actually works, because the devil is in the details, and the details are where speculation either finds grounding or falls apart. When we talk about comet dust affecting Earth, we're talking about specific physical processes that obey well-understood laws, and those laws place hard limits on what's possible. Start with the comet itself, a kilometer-scale ball of ice and rock tumbling through space. When sunlight hits the surface, the ice absorbs energy and sublimates, going directly from solid to gas. This isn't a gentle process. The expanding gas creates pressure that breaks apart the surrounding material, lifting dust grains off the surface and carrying them into space. Think of it like a geyser, except instead of water vapor, you're dealing with carbon dioxide, water vapor, carbon monoxide, and various other volatiles, all mixed with dust particles ranging from smaller than bacteria to the size of gravel. Once these particles are in space, they're subject to several forces. Gravity from the comet nucleus pulls them back, but only weakly. Solar radiation pressure pushes on them, and this pressure is stronger for smaller particles because they have more surface area relative to their mass. The solar wind, that stream of charged particles constantly flowing out from the sun, exerts pressure too. And if the dust grains themselves become electrically charged, they start to interact with magnetic fields, adding another layer of complexity. So how do dust grains become charged? Solar ultraviolet light is energetic enough to knock electrons out of atoms, a process called photoionization. When a dust grain is hit by UV photons, electrons can be ejected from its surface, leaving it with a net positive charge. The solar wind, which consists of electrons and protons, can also contribute by depositing or removing charge depending on the local plasma environment. Dust grains in space typically end up with a charge, and that charge varies depending on their size, composition, and location. Charged dust grains don't move in straight lines anymore. They respond to electric and magnetic fields. In the complex electromagnetic environment near a comet, where you have the solar wind interacting with the comet's gas and dust, you can get interesting collective behaviors. Dust can align along magnetic field lines. It can form structures. In extreme cases, you can even get a kind of plasma crystal where charged grains arrange themselves in regular patterns due to electromagnetic forces. But here's the critical question. When these charged dust grains are spread out over millions of kilometers along a comet's orbital path, what happens when a planet like Earth encounters them? To answer that, we need to look at Earth's magnetosphere, that magnetic bubble that surrounds our planet and shields us from the worst of space weather. Earth's magnetic field extends tens of thousands of kilometers into space on the sunward side and stretches into a long magnetotail on the night side. This field traps charged particles, creating the Van Allen radiation belts where protons and electrons spiral along field lines. When charged particles from space enter the magnetosphere, they can get caught in these structures, bouncing back and forth between the poles. If enough particles enter at once, you get a geomagnetic storm, which can disrupt satellites, cause auroras, and in extreme cases affect power grids on Earth's surface. The solar wind constantly delivers charged particles to Earth's magnetosphere. During quiet conditions, the flux is manageable. During solar storms, it increases dramatically, and we see the effects. So, could comet dust contribute to this? Theoretically, yes. Practically, the numbers matter. A typical meteor shower happens when Earth passes through the debris trail of a comet, and during peak activity, we might see dozens or even hundreds of meteors per hour. That sounds like a lot, but spread over Earth's entire cross-section, it's an incredibly sparse rain. Each cubic kilometer of space in a meteor stream might contain one dust grain. The density is absurdly low, and most of those grains are tiny, micrometers in size, with masses measured in micrograms. When they hit Earth's atmosphere at tens of kilometers per second, they burn up in a flash of light, depositing their kinetic energy as heat and ionizing the air around them. That ionization is real and measurable. Sensitive instruments can detect changes in the ionosphere during meteor showers, temporary increases in electron density at altitudes of 80 to 100 kilometers. Radio signals can reflect differently off these ionized patches, which is why amateur radio operators sometimes get excited during major meteor showers. They can use the ionized trails to bounce radio waves to receivers beyond the normal horizon. But these effects are minor and temporary. They don't affect global atmospheric chemistry. They don't alter weather patterns. They don't trigger earthquakes or volcanic eruptions. The energy involved is simply too small compared to the natural variability Earth experiences. Now, 3I Atlas is unusual because it's interstellar, and there's a question about whether interstellar dust might have different properties than solar system dust. Maybe it's been processed by cosmic rays during its journey through the galaxy, altering its composition or structure. Maybe it carries isotopic signatures from supernova explosions that enriched the interstellar medium. Maybe its crystalline structure is different because it formed under different conditions. All of those maybes are scientifically interesting, and studying samples of interstellar dust would be incredibly valuable for understanding the galaxy beyond our solar system. But different composition doesn't necessarily mean different behavior when it comes to interacting with Earth's atmosphere and magnetosphere. The fundamental physics of charged particle motion in electromagnetic fields doesn't change. The energy scales don't change. A micron-sized dust grain moving at 20 kilometers per second carries a certain amount of kinetic energy regardless of whether it was born around our sun or a star 50 light-years away. If there were going to be measurable effects from Earth passing through 3I Atlas's debris trail, what might we actually see? The most plausible scenario involves subtle increases in noctilucent clouds, those wispy, silvery clouds that form at the edge of space when water vapor freezes onto dust grains in the mesosphere. Comet dust can seed these clouds, and there have been historical correlations between comet appearances and noctilucent cloud activity. It's a minor atmospheric phenomenon, beautiful but not dangerous. We might also see a slight uptick in radio interference at certain frequencies if the ionization level in the upper atmosphere increases. Amateur astronomers and radio enthusiasts might notice anomalies, but again, nothing that would affect everyday life. Satellites might detect a small increase in particle impacts, but they're designed to handle the normal flux of micrometeorites, so even a modest increase wouldn't be problematic. The fringe theories talk about geomagnetic disruption, electromagnetic induction triggering seismic activity, even effects on human consciousness or electronic systems. None of these have any basis in established physics. Geomagnetic storms from the sun, which are far more energetic than anything a comet could produce, don't cause earthquakes. The idea that dust grains could electromagnetically induce current in Earth's mantle sufficient to affect tectonic activity is physically nonsensical. The energies are wrong by many orders of magnitude. So where does that leave us? With a situation where science says don't expect anything dramatic, but where the novelty of encountering an interstellar object's debris trail means there's still room for surprise. Not the surprise of discovering physics is wrong, but the surprise of measuring something subtle and interesting that we haven't seen before. And as 3I Atlas continues its journey outward, the next big event on the calendar is its encounter with Jupiter, a gravitational giant whose influence could reveal even more about this mysterious visitor. March 16th, 2026. Put that date in your calendar. That's when 3I Atlas is scheduled to pass through Jupiter's gravitational sphere of influence. And for astronomers, this is like Christmas morning. Forget Earth. Jupiter is where the real show might happen. To understand why this is such a big deal, you need to appreciate what Jupiter is. It's not just the biggest planet in our solar system. It's so massive that it almost became a star. With 318 times Earth's mass, Jupiter's gravitational pull dominates the outer solar system. Its gravity shapes the asteroid belt, influences comet trajectories, and has acted as a cosmic vacuum cleaner for billions of years, capturing or deflecting objects that might otherwise have struck the inner planets. When something approaches Jupiter at high speed, the dynamics get complicated fast. 3I Atlas is on a hyperbolic trajectory, moving at roughly 58 kilometers per second relative to the Sun. That's about 36 miles per second. Fast. Ridiculously fast. When it enters Jupiter's Hill sphere, the region where Jupiter's gravity dominates over the Sun's, that velocity relative to Jupiter will determine exactly how the encounter plays out. Orbital mechanics is all about energy and momentum. An object on a hyperbolic orbit has more than enough energy to escape the gravitational pull of the body it's passing. It's not going to be captured, but it will be deflected. Jupiter's gravity will bend the comet's path, changing its direction and possibly its speed relative to the Sun. The exact details depend on how close the approach is and the angle of encounter. Current projections suggest the closest approach won't be dramatically close, not like Comet Shoemaker-Levy 9, which got so near Jupiter in 1992 that tidal forces literally tore it into fragments. Those fragments orbited Jupiter for 2 years before crashing into the planet's atmosphere in July 1994, creating impact scars visible from Earth through backyard telescopes. That was a once-in-a-lifetime event for planetary scientists, a chance to see what happens when large objects collide with a gas giant at cosmic velocities. 3I Atlas isn't going to collide with Jupiter. Its trajectory will carry it past the planet at a safe distance. But even a distant encounter is scientifically valuable. By precisely tracking the comet's path before and after the flyby, astronomers can measure the gravitational deflection with incredible accuracy, which provides data for refining models of Jupiter's mass distribution and gravitational field. More interesting is what might happen to the comet itself. Jupiter's gravity is strong enough to stress the comet's nucleus, potentially causing cracks or triggering new outgassing events. We might see sudden brightening as volatile-rich pockets are exposed to sunlight, or as mechanical stress causes the surface to fracture. There's even a possibility, though it's considered unlikely, that the comet could fragment, breaking into smaller pieces that would then follow slightly different trajectories outward from the solar system. If fragmentation occurs, we'd have a situation where one interstellar object becomes several, each carrying away information about the comet's internal structure. Some fragments might be icy, others rocky, depending on how the nucleus was put together. Studying these fragments would be like having a free autopsy of an interstellar comet, revealing layers and composition in ways that are impossible when the object is intact. There's also the wild card of Jupiter's magnetosphere, which is enormous. It extends several million kilometers into space, far enough that Jupiter's moons, Ganymede, Europa, and Callisto orbit within it. This magnetosphere is filled with trapped charged particles, creating intense radiation belts that are deadly to electronics and living tissue. The radiation environment at Jupiter makes Earth's Van Allen belts look like a gentle breeze. When 3I Atlas passes through or near this magnetosphere, the charged dust in its coma and tail will interact with Jupiter's magnetic field. We might see auroras, not on Jupiter itself, but in the cometary material, as particles spiral along field lines and collide, emitting light. Radio emissions could spike as accelerated particles create electromagnetic waves. If the comet has a significant ion tail at the time of encounter, that tail could be bent or disrupted by Jupiter's field, creating visible distortions. The Juno spacecraft, which has been orbiting Jupiter since July 2016, might be positioned to observe the encounter. Juno carries instruments for studying Jupiter's magnetosphere, gravity field, and auroras. If mission controllers can arrange the right orbital geometry, Juno could provide close-up data on the interaction between the comet and Jupiter's magnetic environment. That would be unprecedented, giving us direct measurements instead of having to infer what's happening from Earth-based telescopes. Ground-based observatories will certainly be watching. The encounter offers a chance to study an interstellar comet under completely different conditions than we've seen before. Near the Sun, the dominant forces were solar heating and radiation pressure. Near Jupiter, gravity and magnetic fields take over. Seeing how the comet responds to this different environment will tell us about its structural strength, composition, and dynamical behavior. There's also a speculative scenario that captures imaginations, though it's scientifically unlikely. Could 3I Atlas shed material that gets captured into orbit around Jupiter? Could fragments become temporary satellites? The physics makes this extremely difficult. To go from a hyperbolic trajectory to an elliptical orbit requires a huge change in velocity, far more than could be achieved by simply passing near Jupiter. You'd need an additional force, like atmospheric drag if the object entered Jupiter's upper atmosphere, or a collision that absorbed momentum. But, and this is where speculation gets fun, Jupiter's Trojan asteroids exist at gravitational balance points called Lagrange points, regions where the combined gravitational pull of Jupiter and the Sun create stable positions. Objects can get trapped in these regions and remain there for millions of years. If a fragment of 3I Atlas were ejected with just the right velocity during the encounter, in just the right direction, it could theoretically end up in one of these stable zones. The odds are astronomical, pun intended, but not precisely zero. Even without capture, the flyby will permanently alter 3I Atlas's trajectory. After leaving Jupiter, the comet will head out of the solar system with a different velocity and direction than it had coming in. Over thousands or millions of years, that change could determine which star it passes next, which interstellar clouds it traverses, where it ultimately ends up in the galaxy. Jupiter's gravity, in that sense, is like a signpost changing the comet's cosmic address. And for those of us watching from Earth, the encounter represents something more than just physics and data. It's a reminder that our solar system is not isolated. Objects from other stars can pass through. When they do, our own planets influence them, leaving our mark on something that came from light years away. 3I Atlas arrived carrying information about another stellar system. When it leaves, it will carry information about ours. In a way, it's a message in a bottle, thrown across interstellar space, touched by our sun and planets, then continuing its journey through the galaxy. Step back for a moment and consider what we're really talking about here. 3I Atlas is only the third confirmed interstellar object to pass through our solar system in recorded history. That's not because such visits are rare. It's because we only recently developed the technology and observational programs to detect them. Before 2017, interstellar objects were theoretical, mathematical predictions based on models of how stars form and how planetary systems eject leftover material into the galaxy. We knew they had to exist, but we'd never seen one. Then came Oumuamua in October 2017, spotted by the Pan-STARRS telescope in Hawaii. That discovery changed everything. Suddenly, interstellar objects weren't theoretical. They were real, detectable, and weird. Oumuamua was tumbling, elongated, reddish, and exhibited a small but measurable non-gravitational acceleration that couldn't be explained by outgassing in the normal way. Multiple papers tried to explain it. Avi Loeb suggested it might be an artificial light sail. Others proposed exotic ice sublimation mechanisms or fractal dust aggregates. The debate continues, unresolved. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered the second interstellar visitor, which became Comet 2 I/Borisov. This one looked like a regular comet, with a coma and tail, and its behavior matched expectations for a natural object. It was reassuring in a way. Not everything from interstellar space has to be mysterious. Some things are just comets, following the same physics whether they formed around our sun or someone else's. Now, we have 3I Atlas, and it's stirring the pot again with its unusual composition and anomalies. The pattern emerging is that interstellar objects are diverse. They come in different types, with different properties, reflecting the vast range of conditions under which planetary systems form across the galaxy. Each one is a data point, a snapshot of what exists out there in the cosmic dark between stars. But here's the thing that should make you pause. We've only detected 3. Statistical models, based on their discovery rate, suggest that at any given time, there might be thousands of interstellar objects passing through the inner solar system, most of them too small or too faint for our telescopes to spot. Oumuamua was only discovered after it had already passed perihelion and was heading outward. We caught it on the way out by chance. How many others have we missed entirely? The Vera C. Rubin Observatory, currently under construction in Chile, will change this dramatically. Starting in about 2025 or 2026, its wide field survey will scan the entire visible sky every few nights, detecting faint moving objects that current surveys miss. Estimates suggest it could find dozens of interstellar visitors per year. In a decade, we might have a catalog of hundreds, enough to start doing real statistics on their properties and origins. These objects are cosmic envoys, carrying information about the galaxy that we can't get any other way. When you observe a distant star, you see light, and from that light, you can deduce the star's temperature, composition, and motion. But you can't touch it. You can't sample it. Interstellar objects are different. They're matter from other stellar systems delivered right to our doorstep. If we could land a probe on one, return samples to Earth, we'd have pieces of another star's planetary system in our hands. That possibility has driven serious proposals for interstellar object intercept missions. The challenge is speed. By the time we detect an interstellar visitor, it's usually moving so fast that no existing spacecraft could catch up. You'd need a launch vehicle ready to go at a moment's notice, and you'd need propulsion far more powerful than current chemical rockets. Nuclear propulsion, solar sails, or some other advanced technology would be required. The scientific payoff would be enormous. Imagine analyzing the isotopic ratios in interstellar ice, measuring noble gas abundances, studying organic molecules that formed around a different star. We could constrain models of stellar nucleosynthesis, planetary formation, and even the distribution of life's building blocks across the galaxy. One sample from an interstellar comet could answer questions that decades of astronomical observations cannot. But beyond the science, there's something philosophically profound about these visitors. They connect us to the broader galaxy in a tangible way. They remind us that stellar systems are not isolated islands. Matter flows between stars, carried by rogue planets, comets, asteroids, even molecular clouds. Over billions of years, this exchange has mixed and redistributed material across vast distances. The atoms in your body, forged in stars and dispersed by supernovae, have probably been part of multiple stellar systems over cosmic time. We are, quite literally, made of star stuff that has traveled. Interstellar objects might also be vectors for panspermia, the hypothesis that life or its precursors can spread from world to world. If an interstellar comet carries complex organic molecules, amino acids, or even dormant microbes protected in ice, and if that comet eventually crashes into a planet with suitable conditions, could it seed life there? We don't know. But the fact that comets from other star systems can reach us means the reverse is also true. Earth, over billions of years, has been hit by countless asteroids and comets. Some of those impacts were energetic enough to eject material into space. Could rocks from Earth carrying microbial life have been scattered across the galaxy? Could we have relatives on worlds orbiting other stars, descendants of terrestrial life that hitched a ride on impact ejecta billions of years ago? These questions sound like science fiction, but they're being taken seriously by astrobiologists. The universe might be more connected than we think, with life spreading not through intelligent spacefaring civilizations, but through natural processes, rocks and ice thrown between stars over eons, waiting for the right conditions to bloom. 3I Atlas fits into this grand narrative. It's not just a comet. It's a piece of the galactic ecosystem, a traveler carrying stories from distant realms. Whether it affects Earth's atmosphere or not, whether it fragments at Jupiter or not, it represents something bigger. The ongoing exchange between worlds, the slow mixing of matter, and maybe life across the cosmos. We're watching one chapter in a story that has been unfolding since the first stars ignited and forged the elements that make everything we see. While 3I Atlas captures headlines, the broader revolution in our understanding of the cosmos is accelerating in every direction. The science happening right now, parallel to this one comet's journey, is reshaping how we think about our place in the universe, and it's worth zooming out to see the bigger picture. Artificial intelligence is transforming astronomy in ways that would have seemed impossible a decade ago. Machine learning algorithms are now scanning telescope data, identifying transient events, classifying galaxies, and discovering anomalies faster than human astronomers ever could. When it comes to detecting interstellar objects, AI is becoming crucial. These objects move against the stellar background, creating patterns that automated systems can spot in vast datasets. The algorithms learn what a distant asteroid looks like, what a comet looks like, and what doesn't fit either category. That's how you catch the weird ones, the objects that don't behave according to the standard rules. The implications extend beyond just finding more visitors. AI can help predict where undiscovered objects might be lurking based on gravitational perturbations, gaps in observed trajectories, and statistical patterns. We're moving toward an era where we don't just catalog what we stumble across. We actively hunt for specific types of objects predicted by theory, but not yet seen. It's the difference between fishing with a net and fishing with sonar and targeted lures. Speaking of unexpected discoveries, the field of rogue planets has exploded in recent years. These are worlds that don't orbit stars, having been ejected from their birth systems through gravitational interactions, or never having been bound to a star in the first place. Initial estimates suggested rogue planets might be relatively rare, but newer surveys using gravitational microlensing and direct imaging have found them everywhere. Some estimates now suggest there might be more rogue planets in the galaxy than there are stars. Think about that for a second. Planets, completely dark, tumbling through interstellar space, potentially harboring subsurface oceans kept liquid by residual heat from their formation or radioactive decay. Some could be larger than Jupiter. Others might be Earth-sized or smaller. A few could even retain atmospheres thick enough to provide surface pressure and insulation. The galaxy might be full of wandering worlds, invisible nomads crossing the spaces between stars, occasionally passing through solar systems like ours. Could 3I Atlas itself be related to a rogue planet encounter? Could it have been ejected from its birth system by a close pass with a massive wandering world? The orbital velocities and energy distributions fit models where planetary systems eject material through chaotic gravitational interactions. Every comet, every asteroid we see from interstellar space is a refugee from some ancient dynamical upheaval, tossed into the void by forces we can barely imagine. Dark matter, that invisible substance making up 85% of the universe's matter, remains one of physics' greatest mysteries. But recent work has focused on mapping dark matter structures in our cosmic neighborhood. Using gravitational lensing, stellar kinematics, and sophisticated simulations, astronomers are building three-dimensional maps showing how dark matter is distributed in the Milky Way. These maps reveal something fascinating. Dark matter isn't smooth, it's clumpy, forming halos and streams and concentrated nodes. Our solar system moves through this dark matter as we orbit the galactic center, and the density varies depending on where we are in our orbit. Some theories suggest that fluctuations in dark matter density could influence comet trajectories at the edges of the Oort cloud, occasionally nudging objects inward toward the sun. Could interstellar objects be affected too? Could their paths through the galaxy be shaped not just by stars, but by dark matter's invisible hand? The heliosphere, that bubble of solar wind surrounding our solar system, is getting a fresh look thanks to recent data from the Voyager probes and other missions. We're learning that the boundary between our sun's influence and interstellar space is complex, dynamic, and affected by the local interstellar medium in ways we didn't predict. When an interstellar object like 3I Atlas enters the heliosphere, it transitions from the galactic environment to the solar environment, and that transition affects how solar wind and radiation interact with the comet's coma and tail. So, where does all this leave us, standing here in early January 2026, looking up at a sky that contains an invisible trail of dust from another star system. It leaves us in a moment of genuine scientific uncertainty. Not the kind of uncertainty that justifies panic, but the kind that justifies attention. We don't know exactly what will happen when Earth drifts through the region where 3I Atlas passed. The models say probably nothing dramatic. History says comet dust is benign. But this is the first time, maybe the first time in human history, that we're knowingly passing through an interstellar object's wake with the instruments to detect subtle effects if they exist. Spring 2026 might be completely ordinary, indistinguishable from any other spring. Or it might be the season when sensitive instruments pick up anomalies that don't quite fit expectations, when photographers capture unusual auroras, when atmospheric scientists notice fluctuations they can't immediately explain. Those anomalies, if they appear, won't be catastrophes. They'll be data. New information about how the universe works, about how interstellar material behaves, about what happens when worlds collide, not physically, but in the overlapping of their orbital paths and the mixing of their matter. And then, in March, when 3I Atlas reaches Jupiter, we'll get another chapter in this story. The interactions between an interstellar visitor and a giant planet's magnetosphere, gravity, and radiation belts might teach us things we couldn't learn any other way. Even if nothing unexpected happens, the observations will refine our models and prepare us for the next interstellar visitor, and the one after that, because now that we know how to find them, they're going to keep coming. The galaxy is a busy place, and our little corner of it is right in the middle of ancient currents of matter flowing between stars, mixing and redistributing the elements, perhaps even carrying life across light years and eons. 3I Atlas didn't just pass us by. It connected us, briefly, to some distant stellar system where ice and rock condensed billions of years ago, where the chemistry was just different enough to produce that strange carbon dioxide signature, where dynamics eventually tossed this frozen traveler into the galactic void. Now it's here, touching our world, leaving traces we're only beginning to measure, before continuing on a journey that will take it past other stars, through other systems, maybe never to return to this region of space. It's a visitor, a messenger, and a mystery. And whether it leaves behind anything more than dust and data, it leaves behind questions that will drive discovery for years to come. We are living through a rare moment, one of those times when the universe reminds us that we're not just observers but participants, swept up in cosmic currents far larger than ourselves, connected to stars we cannot see by matter we can barely detect, travelers on a planet that itself is just another wanderer in the endless dark.